All right, so go ahead and respond to the online poll if you haven't done so. And then, and in week 10, I've posted this document that says 102A 2019 winter final exam topics. And so, so this is up there, and I will talk through this, and I'll answer any questions you have about the final exam now. But after today's class, I will not answer. I will not answer any more questions about the final exam. So if you have questions about it, after I go through this, or what, as I'm going through, you can ask questions. Okay. So the final exam will be in this classroom right here at our designated time, which I think is Wednesday at 11:30 a.m. Okay, and so that will be here. The exam will be written for 2 hours and 50 minutes. That gives me a little bit of time to pass out and collect exams. I'll send out a seating chart as usual, things like that. Okay, stuff. It's going to be handwritten. Okay, and this is what you need. You need a calculator. Okay, absolutely. Be sure you bring a calculator. If you forget a calculator, you're going to be in trouble. Okay, any calculator is fine. Graphing calculator, scientific calculator, just nothing that connects to the internet, okay? So you can't use your computer, iPad, or phone, or whatever, okay? You'll also need a straight edge or ruler, okay? Please, if you don't have a ruler, go to the store, spend 50 cents, 75 cents, buy a ruler, okay? Don't come with expecting to use your, don't use like your Bruin card or I don't know, the edge of your calculator as a straight edge or something, okay? Your graphs will come out bad. I'm not going to be able to see what you're trying to draw on your graph. You're not going to get your points, things like that, okay? Just, if you don't have one, you've got a week to go out and buy one, okay? And then I recommend pencil and eraser, okay? That way, if you do something wrong, you can erase your wrong answer, okay? You'll lose points if you try to provide multiple answers and I have to figure out which one you intended. Okay. All right, so I'll go through kind of the topics that you can expect to see, these questions. This will be it, and there's no surprises here, okay? I won't deviate from what I've written here, okay? So there's going to be some floating point arithmetic questions, kind of like stuff that was covered in homework 5, where it'll be like you've got this many bits for the exponent, this many bits for the mantissa. Based on that, what's the biggest number you can store that's not infinity, or what's the smallest this, or how is this going to be written out in bits and things like that. Okay, very similar to what you saw in your homework 5, the floating point stuff there. Okay, any questions on that? Okay, then I will give you a root finding numeric method problem. Okay, be familiar with all of the root finding methods that we've covered in class, and that includes fixed point iteration, the Newton-Raphson method, secant method, and bisection method, okay? And so, just kind of an example problem. I say here's a function, f of x is x cubed minus 4x squared plus 2. And then I provide a graph of the function. All right? And then, and I'll say use some kind of method, right? So here, this example, I say perform 2 manual iterations of Newton-Raphson method to approximate a root of f of x starting at x0 equals 5. Obviously, depending on the different algorithm, I'll give you the necessary starting point. So if it's secant method, I'll give you the kind of x0 and x1, and if it's bisection, I'll give you kind of an x left and an x right. Fixed point, you'll have an x0 and things like that. Okay, and then you'll use the algorithm to figure out x1, and then you'll use and then you'll round off just to kind of keep things easy. You'll round off x1 to 3 decimal places, and then you'll use your rounded value for the next iteration, x2. Okay? and then this is where the ruler comes in. You'll draw any kind of lines necessary, whether that be tangent or secant lines, to show kind of where the next iteration goes. Okay? Are there any questions there? No? This is good? Okay. You'll have a optimization problem, unidimensional optimization problem. And so be familiar with all of the optimization methods we've covered, which is basically root finding applied to a derivative, okay, or golden section search. Okay, so here's an example where I've got another function, and I say find a local max between this and this using golden section search, and find your x1 and x2, choose the boundaries to keep, and round those results to 3 decimal places, and then perform a second iteration and things like that. Okay. If the question is root finding applied to a derivative, I expect you to be able to figure out your derivatives. It might be a long time since you've taken 31A or your univariate calculus class. Okay, so maybe you need to review. The problem I provide will not be too crazy. Okay, so it could contain polynomial terms, basic trig functions, and that means sine, cosine, and tangent. Okay, I won't give you things like arcsine or hyperbolic functions or things like that. Okay, it might have e to the x, and it might have log x, or some kind of product or quotient of those functions. Okay, so review your derivatives for those things. Make sure you know chain rule, product rule, and quotient rule. Okay, and that should be fine. All right. I think a couple quarters ago I had a problem that had sine of x in there, and they asked me what's the derivative of sine of x, and I said I cannot. You can't ask me that question. I can't. So don't. So make sure just your basic things, right? It's not too crazy, but just you got to be able to do some basic derivatives, so that if I ask you to do root finding applied to a derivative, or if one of these things is Newton-Raphson, you got to be able to find the derivative, right? So, okay, any questions there? Sorry, this line D should be indented into here on the calculus review. That's okay? No questions. All right. Number 4, you'll have to do some manual iterations of coordinate descent on a 2-dimensional function. And so I will provide a 2-dimensional bivariate polynomial function. Okay? So that will not have any trig functions or anything in there. It's just going to be, x and y, or some product of those x squared, y squared, or something, some kind of polynomial function, and then you'll perform 2 complete iterations of coordinate descent. So I'm going to give you a starting point, x0, y0, and then you'll have to figure out x1, y1, x2, y2 in the according to coordinate descent. So I'll say start by holding y constant, create a univariate function, optimize it, and so in that case, to optimize, you'll just use calculus to figure out where f of x is equal to 0, right? So if you hold y constant, it becomes a function of f of x only, and then you just do basic calculus to figure out where your derivative equals 0, update x with the correct value, and then you continue. Okay, and then you'll plot each update on the graph, and so you'll get kind of the stair-step picture that looks similar to what you did in homework 5. Okay, and so again, you'll need your ruler there. All right. Is that okay? Questions on that? Yeah, I have you do all of these manual things because sometimes when you do stuff with the code, what's happening gets a little bit lost. And so I figure if you can do these things manually, you have an understanding of how these algorithms work. And if you were forced then to code it up, you'll know how the algorithms work, and you can code it up accordingly. Okay. No cheat sheets or note sheets. You got to learn and internalize these methods. All right, and then you'll have a question on a randomization test question, okay? So I'll describe some kind of scenario, and then I'll also provide kind of what kind of data was collected, and the data could be categorical, kind of like the yawning problem that we saw in with Mythbusters, or it could be numeric. So in your homework you have like parking lot data, waiting times, and stuff like that. And either of those could be used for a randomization test. And then I'll have some kind of question using that requires a hypothesis test, such as, is there evidence that a seed yawn increases the chance of a person yawning, or is there evidence that drivers take longer to exit their space if a person's waiting on them? And based on that description, you'll need to decide what kind of hypotheses to use, right? Whether it's a one-sided or two-sided hypothesis test. Both of these are one-sided, right? Because it says, does yawning increase the chance of someone else yawning, or does someone take longer? So in those cases, you have a direction in your alternative. But the question might be, is there a difference or something? And you need to recognize that that'd be two-sided. And then you will write code by hand, manually write some code by hand to perform a randomization test, okay? Your code needs to be written clearly and legible, and it needs to be correct. And then you've got to make sure you include some kind of line to calculate or find the empirical p-value. And maybe that requires you to know whether you need to use the absolute value or not. There, okay? And then, of course, you're not going to be able to actually run the code. You don't have a computer. But I'll write something like, let's pretend that the resulting p-value from your empirical p-value calculation is 0.23. Based on that, what kind of conclusion do you make regarding the null hypothesis and stuff like that? So that's the randomization test. And then I might ask you to do it, or not might, I will ask you to do a bootstrap test, okay? And then bootstrap test, again, I'll have a scenario, the data, question that requires a hypothesis test, much like the randomization test, okay? But for the bootstrap, it could be parametric bootstrap, it could be non-parametric bootstrap, okay? And if it's non-parametric, be ready to use either package boot or writing out the code yourself by hand, okay? So if it's, and if it is, and I will tell you whether I want you to do parametric or non-parametric. And if I tell you it's going to be parametric, I will tell you which distribution to use, whether that be R norm or some other R exponential or whatever it might be. I will tell you which what distribution to use, but you'll have to write the code for figuring out how the bootstrap should be done. And then you'll write your code. You'll perform to perform the test. Again, your code needs to be correct, and you got to be able to find the empirical p-value. And then just like in the randomization test, I'll say, let's pretend that the resulting p-value is this, and I'll ask you what kind of conclusion you're supposed to make. Okay. Any questions on that? No questions. All right. And then the last bit, there's just going to be a few questions, a handful of questions, covering kind of some of the conceptual parts, the numeric and computational methods. So, for example, I might have a question, kind of a question that I'm talking about is like, when will Newton's method for root finding fail? Okay. And so it fails when the derivative doesn't exist, or it fails if the derivative equals 0, or also could fail if the sequence results in some kind of loop, okay, where you take the derivative or you take the next iteration and it sends you back to kind of where you started from, and that could happen as well. Or another example is what has to be true about the data in order to use a randomization test, and what has to be true about the data. exchangeability, right? And what does exchangeability mean? It means every permutation of the assignment of treatments is equally valid under the null hypothesis. Stuff like that, okay? I'm not going to tell you exactly what questions I'm going to ask, but just be prepared for some of those types of questions. Okay, and that's it. All right, that's no surprises. What you see listed here is exactly what you will see on the final exam. Just an actual problem, not just a description of the problem. And then so there's no need to review things like scope or data structures from the first half of the course. Okay, as far as the R that you need to know how to write the R code for the randomization and bootstrap tests, okay? And that code that you write has to be correct, okay? And you'll lose points if the code you write is wrong, or there's errors in the code that you write. So make sure that the code you write for that part is correct. Make sure when you write your code, it's legible, okay? And then I think I've provided a lot of information here. And so you should be able to write practice questions for each other if you want, for each other on Piazza, okay? And I think that's probably the best way to study and prepare for the exam is you write out some practice questions, solve them yourself, okay? But that said, I'm not going to answer any questions about the final exam on Piazza, okay? This is the document you get that describes the final exam, and this is it. And if you have questions, now's the time to ask them, and I will answer. But after today's class, I'm not going to answer any more questions about the final on Piazza. So I'll send out a seating chart, all of that. I'll record participation points on Friday of this week, okay, for Piazza, and then I will shut down the class Piazza on the morning of the final exam, okay, at 10 o'clock. So so that means you can write stuff between Friday and Wednesday, but you just won't get points for it on your Piazza. Don't come to me complaining about that. And I think that's it. Okay. Any other questions? Yes.
How many questions will you put on the final?
It will be pretty much this. Okay, so you can expect like basically a page for each of these questions. Okay, so like seven. I mean, I don't know. Like, will you count 7 as like multiple questions or like one question, right? So you have kind of these. So this is it. Okay, you will see a problem for each of these things that I've listed out here. Okay, yeah, question.
Oh, so for the randomization and bootstrap test problems, are you gonna tell us which test we'll have to do, or do we have to figure out?
I guess I'll say do a randomization test here. Yeah, I'm not sure. It would be nice if I could write a question that doesn't do that, but then I feel like no matter what I like, it's going to give it away. Like, it should be clear from the question what you need to do. Okay, I might not say explicitly do this or do that, but it should be clear, right? So, but yeah, randomization test, bootstrap test. Okay, and just yeah, I guess for the bootstrap test, I will tell you like. I want you to use package boot, or I want you to do parametric bootstrap or something. So it'll be clear because I can do that. So just be ready for any of these methods, specific methods to be, you have to use this, right? So I'm not going to tell you which method I'm going to right now, but on the test it'll say use this particular method, and just be ready for any of these to show up. Yes, question. Yeah. I'll say, your resulting p-value is this, and I'll say, I guess, assuming an alpha of this level. Yeah, that's fine. Is that good? Okay. Last class, some students just had some questions about what kind of conclusions do we make based on the p-value and alpha, and then we got into a little bit of a talk about alpha and what alpha means and a discussion there, and I guess I'll go over this briefly, okay? Unless there's other topical questions that you want covered. Okay, all right. So simple answer regarding p-values and alpha. If the p-value ends up less than alpha, you say we reject the null. And if the p-value ends up greater than or equal to alpha, you do not reject the null. I'll write, do not say we accept the null, okay? Because that is wrong, okay? Alpha is the significance level, which is equal to the probability of making a type 1 error, which is equal to the probability of a false positive, right? And the false positive means we mistakenly reject the null hypothesis when the null hypothesis is true. I think this is a little just too big here, okay? And so what level alpha reflects our willingness to make this mistake. So when we choose alpha equal to 0.05, it says I'm willing to make a type 1 error 5% of the time, which means, so that says something, right? We never pick alpha to be 0, because if we picked alpha to be 0, so on the other hand, you might say, well, I don't want to make a type 1 error, right? If you don't want to make a type 1 error, which is a reasonable thing to say, it's unavoidable though, okay? Because the only way you can avoid making type 1 errors is to choose alpha to be 0. But if you choose alpha to be 0, you will never reject the null hypothesis, okay? So I write, in general, reducing the risk of type 1 error will result in a higher risk of type 2 error. And type 2 error is the false negative, which means the null hypothesis is wrong, and we should reject it. Okay, but our conclusion is not to reject the null hypothesis. So that's the type 2 error. Okay, so here's an example. In a criminal trial, the defendant is presumed innocent until proven guilty, okay? And so because we're presuming innocence, that means our null hypothesis is that the defendant is innocent, and the alternative is that the defendant is guilty, okay? And so in the ideal world, all innocent people, all innocent defendants are acquitted, okay? We let them go. And everyone who's guilty is convicted, okay? That's the ideal scenario, okay? In the real world, however, we make mistakes sometimes. We don't want to. We don't want to make errors. We don't want to make mistakes, but mistakes happen. So what is a type 1 error in this scenario, and what's a type 2 error? So what's a type 1 error? Okay, false positive. And what does that mean in this case? Okay, we reject the null when the null is true. But with regards to the defendant being guilty and innocent, what does it mean? And whether we convict or acquit, what is a type 1 error? What's that? Yeah, so type 1 error is an innocent person is convicted, okay? So, we send an innocent person to prison. We possibly execute an innocent person, things like that, okay? And that's, we don't want to make that mistake, okay? And then a type 2 error is that a guilty person is let go, okay? We don't want that either, but that mistake can happen, right? Because we don't live in the ideal world. We live in the real world where we try to make the right decision most of the time, but we are also going to make some mistakes because we don't have all of the information. We cannot travel back in time to see exactly what happened when the crime was committed. So it's difficult to know, okay? And also, you know, based on, and it's impossible to know the hearts of man, and so you cannot know the actual intent, right? And because some crimes are based on, you know, what the intent at the time also, and that's also impossible to know. But anyway, our justice system is set up with the assumption that the type 1 error is worse than the type 2 error, okay? And that I think, who was it? That said we'd rather let the guilty people go free than convict an innocent person, and that's what we have. So because the type 1 error is worse, we want to pick a small alpha, okay? Alpha is equal to the probability of type 1 error. We want to reduce the type 1 error because the type 1 error is worse, so we're going to pick a small alpha, okay? And they actually say this when, if you're ever on a jury or whatever, they don't say use a small alpha, but they say something like that. What do they say? There's a key phrase that we hear.
More evidence.
What's that?
More evidence.
Not more evidence. They say you need evidence beyond a reasonable doubt, right? So the level, the kind of the standard for a conviction in a criminal trial is reasonable doubt, okay? Which means, you know, the bar is this high. It's, you know, basically a small alpha. They don't say you have to be 100% sure, because nobody can be 100% sure, so that would result in no convictions ever. But at the same time, they don't want people convicting. I don't know why I'm getting static, so much static. They don't want people convicting because they just have a feeling about the person, or you know, they just don't like the way the person looks or something like that. So they don't. It's evidence beyond a reasonable doubt, right? So that's kind of this whole due process and all of that. This is, you know, public opinion, however. So this is the standard set for criminal trials, but you know, for public opinion, it's much different, right? So on Twitter and things like that, you know, you might not get the type 2 error. I mean, the criminal court might make a type 2 error. They might acquit somebody that everybody feels is guilty or something. But again, it's because they're operating with a small alpha. Okay? And so that if someone says it was in self-defense, that's a difficult thing to overcome in a criminal trial. Okay, here is another scenario, okay? And so we have a person shows symptoms of an illness, and the person is not sure if they should seek medical attention, okay? And so generally we assume people are healthy until they begin to show symptoms. So in that case, the null hypothesis is going to be that the person is healthy, and the alternative will be that the person needs medical attention, okay? So what is a type 1 and what's a type 2 error in this scenario? Type 1 error would be what? Null hypothesis is true, but we've rejected the null. So type 1 error would be a healthy person visits the doctor. The doctor says, you're healthy, you're fine, nothing's wrong with you. Okay? What's a type 2 error? So type 2 would be someone is sick or needs medical attention, but they believe they're okay and they don't visit the doctor. Okay, so someone is actually in need of medical attention, but they think they're fine, they don't go to the doctor. Okay, so which of those errors are worse? The type 2. I mean, both are bad, okay? We don't want either of these things, right? So a healthy person seeks medical attention. Type 2, yeah, person who doesn't go to the doctor. Type 2 error is worse, could be fatal. Type 1 error is, annoying and puts, undue burden on the medical system, on the healthcare system, which we don't want, but the type 2 error is worse, okay? But this is generally speaking, not as bad. Not as bad as type 2 error. Okay, or I guess for the individual, okay, maybe as society at large, the type 1 error is worse. But type 2 error, I don't know. I think type 2 error is worse in all cases, right? So in this case, we're going to choose a large alpha, okay? And I don't know if you guys already saw it, but I'm sure we can think of a website that operates with a large alpha regarding medical advice, right? Or no? WebMD, I don't know if you guys ever visited WebMD to look up your symptoms online, okay? And I think there's jokes and memes, and we know about WebMD that they operate with a very high alpha, right? Anything you type into WebMD, it's going to come back and say, oh my gosh, you might be dying, you might have cancer, you might be pregnant, you might have this kind of disease, and you better seek medical attention. I mean, it's not as extreme as that, but this is kind of like anything you type in there, it's going to come back with all sorts of possible things, and some of those things are very scary sounding. And that's because WebMD is operating with a very high alpha. They figure if somebody's coming to our website for medical advice, and I think there's all sorts of disclaimers that say we're not offering medical advice, but just information. But they're operating with a very high alpha. They'd rather send somebody who's healthy to the doctor rather than getting someone to think that that they are healthy when indeed they are actually sick and in need of medical attention. So that's why WebMD is the way it is, okay? It's not that there's some conspiracy to, I don't know, burden our healthcare system or something. I don't know. Okay. Although, if you operate with too high of an alpha, then operating with too high of an alpha can psychologically cause your alpha to become 0, okay? If that makes sense, right? So, for example, if you keep visiting the doctor too many times, like you go visit WebMD and you say, I'm sick and I've got this problem, and you go to the doctor like a million times, that doctor might become annoyed with you, and then you get into this boy who cried wolf scenario where it could come to a point where you actually do have a problem, but because the doctor knows who you are, for you, they are operating with alpha equals 0, okay? Because your alpha was too high for too long, psychologically they now choose alpha equals 0, and you don't get the medical attention you need. So maybe you have to find a new doctor at that point. I think there was a story about these burglars, and what they did is they found a way to trigger they couldn't figure out how to disable the burglar alarm at a place that they wanted to rob from, but they were able to figure out how to set it off without actually breaking any windows or anything like that. And so they set it off, and the police came to check it out. Nothing was wrong. The police go back. The next day they set it off again, and they did this for like 5 days in a row until on the 6th day, when they set it off, the police did not respond because they said, oh, it's just a false alarm, and that's when they broke in and burglarized the place. So So sometimes operating with too high of an alpha or something like that, because humans don't always make the best decisions, we can suddenly operate with a smaller alpha. Okay, is that all right? Okay, anyway, we'll throw that online. And then, I guess so in this, in the last bit, I was just gonna do a little bit of, I don't know, something that I thought was kind of fun. I mean, this is my idea of fun, which is different from your idea of fun, but we'll go. And we'll talk about kernel density estimation, okay? And so this is what I have here. So what kernel density estimation is it's a way to create a graphic approximation of the underlying probability distribution. Sorry, my handwriting is so messy here. But if you think about what a histogram does, kernel density estimation does the exact same thing as a histogram, except it results in prettier or smoother plots in general than the histogram, okay? So the whole reason why we produce a histogram, okay, is so that we can kind of get an idea of what the underlying distribution is, right? So here, I can generate 100 random points from a distribution, normal distribution, and I create the histogram and it looks like this. There's another 100 random points and it looks like this. And so a lot of these don't exactly look normal because we've got a fairly small sample size of only 100 data points, right? So here's each of these things. Okay, so if we have this, we can create something called a kernel density estimate, which is just done by doing density x, and if you plot the density of x, okay, so again, x is just a vector of 100 values. When you plot the density of x, it takes this histogram and it tries to kind of smooth things out, and you get this kind of plot, and this is supposed to represent maybe what the underlying probability distribution looks like. Okay, so this is just an approximation, or it's kind of like, here's the histogram, draw something that kind of smooths it out, and this is kind of the result that you get. But again, depending on, so here's this histogram, and if I create a density plot here, it looks kind of like this, okay? So you can kind of see where this sticks up a little bit higher than normal. When we try to smooth it out, it looks kind of like this, okay? And you can do this for other distributions, okay? So here's an exponential distribution, which the histogram looks kind of like this. And I can say plot a density, make a density estimate of this based on this data. And it looks like this, okay? Do you guys see any issues or anything wrong with this density estimate? Or what? So if our data comes from an exponential distribution, what's the domain of the exponential distribution? 0 and higher, right? So the support, or the domain of the exponential, I guess the support of the exponential distribution is only where x is positive, and the histogram reflects this, okay? But the density plot seems to produce values that are, kind of slopes off below 0, okay? And this is wrong. We know we actually can't generate any values lower than 0, okay? And that's because we are just doing, it's just this computational method. There's nothing theoretic behind it other than it's kind of what it's trying to do is basically, a computationally more intense method of producing a histogram, but it's using what we call these little kernel estimates here, okay? And so if you think about what a histogram does, is it basically looks at the data points, and where it finds a data point, it basically stacks bricks at each location of a data point, okay? And it says, kind of within this location, this interval, there were 5 data points, so we're going to stack 5 bricks on top of each other, and we get a bar that's 5 units high. And now the next interval, there's like 10 data points, and we're going to stack 10 bricks on top of each other, and we're going to get a bar that's 10 units high. Okay? Kernel density estimation does pretty much something very similar, except you don't have these rigid bricks. Instead, you have these, I don't know if there's an analogous thing in life, but I called it, you have these mounds of sand, okay? You're gonna basically drop mounds of sand at the location of each data point, okay? And we have different options for kind of the shape of the mound of sand that we drop, okay? You can drop rectangle-shaped mounds of sand, or the most common choice is the Gaussian, so kind of this normal hill being dropped up on each kind of data point, this little sand hill. You can drop triangles or upside-down parabolas, which gets this name Exponential, based after the guy who did it. And so I'm just going to kind of illustrate what this looks like with this silly data set, okay? So here my data consists of 2 data points, -1 and 1. And we would never actually do density estimation for a data set with only 2 points, but it is useful in illustrating how kernel density estimation works, okay? And so if we make a histogram, you've got a point, you got a brick at, you know, kind of -1, and then another brick at 1, and things like that. Here, I will just show you the default when we ask for density. What it's going to do is it's going to drop a mound of a normal-shaped, a Gaussian-shaped mound of sand at -1, and a Gaussian-shaped mound of sand at 1. And where those mounds of sand overlap, they will stack on top of each other, okay? So just kind of imagine what this might look like, and it looks like this, okay? So you can see there's kind of a mound of sand centered at -1 and a mound of sand centered at +1, but then there's overlap between the two, and so you get kind of this shape right here, okay? There's this parameter called bandwidth, which states how wide or how narrow you want your mound of sand to be, okay? There's a default calculation for how the bandwidth should be calculated, and you can look this up in the help for the density. So if you look up the density function under the bandwidth, there's a default that says bandwidth.nrd, and bandwidth.nrd says it uses this rule of thumb calculation, which is 0.9 times the minimum of the standard deviation or the interquartile range divided by 1.34 times the sample size to the -1/5 power, okay? That comes from a paper written back in 1986. But anyway, there is a rule for how the bandwidth is chosen by default, but this is just an arbitrary rule, okay? And you can specify the bandwidth yourself. And so let me just kind of illustrate what different bandwidths are, okay? So choosing a different bandwidth will change how wide or how narrow this mound of sand is. And we're just dropping one at each data point. So here I got a mound of sand at -1, 1, and 1. And so when I choose bandwidth equal to 0.2, I get a narrow mound centered at -1 and another mound centered at 1, okay? And if I were to do -1, 0, 1, and I do this, you know, now I've got kind of these three things added up together, okay? But I'm just going to go back to these two, and I just want to show you. I'm going to increase the bandwidth, okay? So we're still going to see the mounds centered at -1 and +1, but because these mounds get wider, the entire picture will get also a little bit wider, okay? So here, maybe I'll do xlim equal to -3 and 3, just so you can see. Okay, so here's our original plot going from -3 to 3, and we have a band plot centered at 0.2, and bandwidth of 0.2, bandwidth of 0.3, bandwidth of 0.4, and you can see where they overlap, you kind of get this, the shape as the mounds get wider and wider, okay? Until, at kind of 1, they've kind of merged together, okay? And as I make it wider, they just start to do that, okay? And again, it's just, you have a hill centered at -1 and another hill centered at +1, but we're just increasing how wide that bandwidth is, okay? You have other options for the density. You can choose the shape of the kernel to be something like rectangular, okay? All right, so here is a rectangular kernel centered of bandwidth 0.3, centered at 1 and -1. They're not exactly perfectly rectangular. They're like ever so slightly trapezoidal, where the base is just a tiny bit wider than at the top, okay? All right, and so let me just show you what happens as I increase the width of these things. So we're still centered at 1 and -1, and at 0.5, I think they get very close. And what will happen at 0.6 when they start to overlap? What will the resulting shape be? As you drop this rectangular amount of sand and another rectangular amount of sand. You get this, because there's kind of just this little bit of overlap, they stack on top of each other. So this is not regular sand that normally spreads out when it hits the ground. This is like magic sand, okay? But I don't know how else to explain this idea, this thing kind of dropping, and when they stack on top of each other, okay? And then, so as I increase the bandwidth, we can kind of see this, I don't know, this top part get wider and wider, okay? And it's just, here's a rectangle over here, and there's another rectangle over there, and where they overlap, you get the thing looks like that, okay? Same with triangles, okay? You can have instead of rectangular kernel, you can have a triangular kernel. So here's a triangle, and as I make them wider, what will happen in the middle? So here's 0.4, and if I go up to 0.5, this side goes down, the other side goes out, up, down in the other direction, and so they kind of overlap, and you get this flat part in the middle. When the thing gets wide enough, you get this kind of this weird shape, right? Okay, and so basically at this point, when we do things like a large distribution or a larger set of data, okay, we are adding 100 of these little normal curves on top of each other, okay? So if, here's a just by random chance, this is the sample of data I collected, and when I plot the density, it ends up looking like that. And we can choose, again, you can choose different bandwidths. You can increase it to like 0.4, and it kind of will smooth things out a little bit. You can leave the bandwidth by default. You can choose the kernel shape to be rectangular, and it's going to drop rectangles at each of these things, which will end up something a little bit more jagged. You can do triangular, which actually seems to smooth things out. And you have all sorts of different options. But kernel density estimation is something that shows up quite regularly and quite frequently as maybe an alternative to a histogram, because it ends up with this smoother looking curve, which some find to be a little bit more pleasing and nicer to look at. Anyway, that covers kernel density estimation. We'll see you guys on Wednesday.